Everyone, welcome back. So last time we had simple cubic structure, which was just atoms at the corners, and now we've added an atom in the middle. Now, if you just look at it visually over here, you can see that because we've added that atom in the middle, well, all of our edge atoms, they've had to move out. Okay, so they all moved out a little bit, but you can see this looks just, visually like it's a lot fuller, like it's a lot more of the space is used. And we see this in a lot of different types of metals. We see in chromium and tungsten, tantalum, molybdenum, and also in iron, and a particular form of iron, which is called alpha iron. Iron can have various different crystal structures depending on how hot it is. So when it's fairly cool, this is the only structure that is stable. Now, look at it over here. This is when we're looking at it from a 3D aspect. You see all these atoms. And what you might realize is that what we're doing is more or less we're having different layers of atoms that are interwoven. So one layer looks like this. And then directly on top of that, let me see if I can, let me go over here. Well, directly on top of that we'll have a second set of atoms. I'll make them in blue. And so they'll look like this. And they will go into the spaces of my previous set. And then we keep on going back and forth, back and forth. It just alternates. A, B, A, B, A, B. Now, because of that, we have a better packing factor. It's not the best, but it's still a good one here. We're just going to keep on going back and forth. Now, let's look at a couple of things. First off, it's coordination number. How many nearest neighbor atoms are there? Well, it's very easy to see from this one right here. How many atoms is that touching? Since it touches one at each corner, the coordination number is 8. It touches 8 different atoms. So we're getting more atoms touching, which means it's going to have a better packing factor, and this is a lower energy system. Second thing is how many atoms are in the cell? Well, last time we had 1 atom because we had 1/8 of an atom at each of these corners. And now we're going to add to that the atom in the middle. We'll have 2 atoms total. 2 atoms total. Now we're going to figure out what the atomic packing factor for this body-centered cubic structure is. Now it's 0.68, so we've gone up. Last time it was 0.52, so we've gone up. This is better. We'll have an even better one next time. But how do we figure this out? Well, the important thing is triangles. You have to figure out those triangles. Now it's not easy to see from here. I can't just use this side A, but I do know that it touches directly from this edge to this edge. So this is 1 radius plus 2 radii plus a fourth radius. So 4 radius goes along this edge. I know that this side right here is A, but what is this bottom angle? What is this bottom line right here? That goes along the bottom of my cube. Well, let's look at it from the top. So I'm going to redraw this from the top. So if I look at it from the top, what I see is the following. This is the diagonal line. I'm looking straight above, and I'm trying to figure out how long it is from this view. I'm looking straight down on top of it. So this side right here is A, and this side right here is A. And if you've done any trigonometry, what you know is that the hypotenuse of a right triangle is simply c squared equals a squared plus b squared. Which, since a and b are the same thing, I can say c squared is equal to 2a squared, or c is equal to square root of 2 times a. Okay, so that is the square root of 2 of a over here, and that would be equal to the bottom. Now I know what the bottom is, I know what the top is, and I can then solve for the hypotenuse. For all these, I'm trying to get some relation that takes me from my radius and puts it in terms of A. Because that's the only way I'm going to be able to figure out the volume of the filled volume in my particular problems. Okay. Now with this, what I do is I put in my equation for the volume of a sphere here. And instead of having the radius, I put in this length right there that I calculated. This right here is the number of atoms per unit cell. We worked that out last time. And the volume of the unit cell is simply a cubed. It's always a cubed. I multiply all this out, I get 0.68. So in short, what happened here is I realized that it's touching along this diagonal line. I counted the number of radiuses to do that. So that's 1 radius, 2 radiuses, 3 radiuses, 4 radiuses, because the diameter is twice the radius. I used that, the fact that I knew this edge length, which is A, and this edge length, which is A, to solve for the bottom. And that gave me that number here. And I already knew A, which is the height. And from that, I could just use some basic trick to use my Pythagorean theorem to solve for this. Okay, and that's it for this time. So I hope you enjoyed, and I'll see you all next time as we go through our last 2 crystal structure types. Have a wonderful day. Bye-bye.